Greetings. We are going to look at using the theorem to find a 2x2 inverse for a 2x2 matrix. Now, other matrices are not as nicely put together to be able to find an inverse like this. We have this nice theorem for this. Other ones get a lot more involved. Also, we need to keep in mind that this is for square matrices. Given some 2x2 matrix with elements A, B, C, and D, then we're going to have an inverse given by this formula, 1 over the product of AD minus BC, and that scalar is being multiplied by the matrix with entries D, negative B, negative C, and A. And these entries here are all in respect to the way we've labeled our original given. Now there's an if statement here that the determinant of D, the original matrix, cannot be 0. If it is 0, then we don't have an inverse matrix for this. The reason for that is if you look down here in the denominator, you see that AD minus BC is actually the determinant for a 2x2 matrix. So if your determinant is 0, that means that you're trying to divide by 0 at this point, and division by 0 is not defined in this algebra. We're going to look at an example 2x2 matrix. I'm going to call this one L, and we're going to have elements 12, 9, 19, and 1, and we want to use this formula to find its inverse. So we're going to call this L to the negative 1 here, and we are going to create our fraction here. That is 12 times 1 will be 12. 9 times 19 is 177, and so we're going to subtract those. Over here in the matrix, we are just flipping the main diagonal here, so this will be 1 here and 12 here. And on this other diagonal, we are just switching the sign. So I have negative 19 and negative 9 here. And we can just run through the simplification now until we get our 2x2 matrix. So we're going to subtract these here. This will be negative 159, and that will be multiplied by the matrix here, which isn't changed at this step. All right, so we're multiplying this scalar times each of the elements in the matrix. For the numbers that are positive, since this is negative, those are going to become positive, and the entries that are negative are going to become positive since this is negative, because we'll have double negatives at that point. So we end up with a matrix that's 1 over 159, 9 over 159, this one's negative, this will be 19 over 159, and 12 over 159, and that will be negative. These are reducible in some areas. Some of these fractions do turn out to be reducible, so you can reduce this matrix to this matrix. And this will be our final result. This will be the inverse matrix of the matrix that we started with over here. One thing you may notice is that we have this rational entry matrix here, and we started out with an integer entry matrix. And that's one thing that tends to happen is if you start out with integer entries, you get an inverse with rational entries. If you start out with a matrix with rational entries, you can get something that's nice with a integer entry. That's just kind of the way that things happen since you have this scalar factor that is a fraction. Again, for the other larger square matrices, they're a lot more involved. It's nice to have this nice theorem for the 2x2. Cheerful calculations.